ultimately control a mouse pointer using only your gaze. And another restriction we have is we can't have too many restrictions. We want it to be like fairly free, like you're just sitting there, so you don't have to put your head a specific way. You can move your head freely, move your eyes freely. So yeah, an important first step is face detection, so you can narrow down a region from which to pick out the eyes and important features. Okay. So this is the process that I use for face detection, which I'll go through in this PowerPoint. First detect the skin, then find some edges, find the largest connected component, and then make a rectangle around that. So the first step for skin detection. I found skin just based on color. There are a couple different methods to do this. I just use like straight boundary regions. I use the HSV color space, which is hue, saturation, and I guess V is value or intensity. So human skin tones, as you can kind of see from there, they fall in like a small range of hue and a certain range of saturation. So as long as you restrict those with like the full range for the V component, that covers pretty much the whole range of human skin tones. So here, I wanted to use a pretty broad range. So like my approach was get more stuff and make sure you do get the skin tone rather than risk not getting the skin tone. Okay. Okay, so probably one of the biggest problems we faced was shiny spots. Due to the lighting conditions in the room and I guess how the webcam is set up, a lot of skin tones just appeared as bright white regions. Like their RGB values were like 248, 248, 248. So we want to make sure these are included as skin pixels, but they don't fall into the hue and saturation values for skin tone. So we had to find a way around this. All right. So the way I did this, for every bright spot, I wanted to see, well, does it have skin tone pixels nearby? Because if you have like a bright spot by your nose or on your forehead or something, even though it is not originally included as a skin pixel, it should have some skin pixels nearby. So the way I did that, I just used a moving average. I used like a 5x5 box. So just for each bright pixel, do a moving average, and if it ends up being greater than 0, that means there's some skin pixel in the vicinity. So you should say, yes, this is a skin pixel. So overall, this worked fairly well because like bright spots around your nose, for example, it got pretty well. I mean, depending on the size of your box, you won't get like all the bright spots in the middle of the forehead, since if it's in the middle, it's just surrounded by other bright spots, not skin tone colors. But also, what it is useful for, like say you have a bright light or something, then that will not be considered skin tone because even though it's bright and it could be skin tone, it's uniformly bright, so it probably isn't. Okay. So after this, we just applied some filtering just to get a cleaner image. First step was apply a couple small erosions just to get rid of like very small salt and pepper noise. Next step was a 5x5 dilation just to kind of close some of the holes in the facial region. Like for example, there are going to be two big holes where the eyes are, maybe the mouth or something. Yeah, so that's just to clean up noise pretty much. Okay, so here are a few images outlining this process. So the first step is just the webcam image. The second step is stuff that's detected as skin pixels without the bright spot thing applied yet. The third step is after you apply the bright spot thing. So what you can see here, some of those like shiny spots by my nose and mouth, they got pretty much completely filled in after the bright spot method. It also got some of the stuff around my forehead, not all of it. Now one problem you can see in this image, I'm wearing a red shirt, so that all got picked up as skin tone, which could create problems. You'll see how I deal with that later. And the last image on the lower right is just after the filtering's applied. Okay, so the next step, edge detection. So the main purpose of this, we're looking for the largest connected component. And one thing that can cause a problem is if there's something that's skin colored adjacent to your face. Like if you remember the disfigured face that I was working with a lot, he had like a kind of skin tone shirt, and that was always getting picked up as part of his face. And a similar thing is in that image with my red shirt. So what we do here, we're just trying to use edge detection to break it up into components if there's two skin colored things that are connected. Okay, so what I did, I used Candy Edge Detector, which is built into MATLAB, And I did edge detection on the grayscale versions of R, G, and B components just to make sure I got as many edges as possible. Because sometimes I was finding if you just turn the image to grayscale, like some edges that are distinct in the color image may disappear in the grayscale image. So this was pretty good in getting a lot of edges. And then we only care about edges that are in the facial region. So if you subtract those from the face binary image, you'll have a facial image with all the edges. Okay, so the next step, I think I have edge pictures later, maybe. Anyway, next step is find the largest connected component. So after you found all the edges, this is built into MATLAB. I use 8 connected, which means if you have like 2 diagonal pixels, it'll count those as connected. And usually, since you're sitting right in front of a webcam, this is going to be the face. So depending on background conditions or maybe other factors, like if you're wearing a red shirt or something, the largest region could be something that's not just your face. It might be a problem. So this is something we'll look at in the future. But for now, this is adequate. It usually gets the face and doesn't pick up too much background junk. So we might add in some geometric verification, like make sure it's roughly oval shaped or something to ensure that it's the facial region. Okay, so here again, that's the original image from the webcam. Then after filtering, this one is after edge detection. So you can see it picks up a lot of edges, which might not always be a good thing, but you can see here in the top right image, the shirt is connected to my face, so that would all be considered one component. But after you break up into edges, and then in the lower right find the largest connected component, it's able to get rid of the red shirt and only have generally the facial region. Okay. Now one other thing you might have noticed there is it's too low because some parts of the eyes and forehead are kind of cut off. They're not included as skin color. I'll mention how I deal with that later on. Okay, so the final step is to find the face rectangle. So after you have this connected component, just get a nice rectangle around the face. So the way I did this, I found the centroid and area of the region, and then I made a rectangle with the same area as that region using the golden ratio. So centered at the centroid, same area as the largest connected component, but just kind of take the junk and mold it into a rectangle. Okay, I also scaled it up to ensure that it includes the entire face because like for the purpose of eye detection, if your face is in a different orientation like that, you want to make sure you always have both eyes in it. So I scaled it up by, I think, a factor of 2. Okay. Oh, and another thing I did here for eye detection that I don't think I mentioned in the PowerPoint is because usually like your neck is skin colored and your lower face is skin colored, but your forehead and eyes might not be picked up. I also shifted it up slightly from the centroid to have a better chance of including your eyes. Okay, so eye detection, this is what I'm currently working on. I don't have something that's always successful yet, but I'll just talk about what I've done so far. So the current approach, the first step is just to find eye candidates based on the color. And since we've already detected the face, we can crop it down to where the eyes should be. And then we don't have that many eye candidates. So yeah, I just look for pixels where like the blue to red plus green ratio beats a certain threshold, because I find that eyes usually have like a fairly bright blue region in them. Yeah. And then once you find the eye candidates, the next step is to try to narrow it down to a single pair of eyes. And I have a few different tests to do for this. First, I get rid of regions that are too big or too small to be eyes, like given the resolution of the image. I also check the skin percentage in the surrounding region. Like for example, your hair might have some blue color to it, but like your hair is less likely to be surrounded by skin, like just a little bit here, but not on the other side. The eye region should be pretty much surrounded by skin color, so that's another way to narrow it down. And then I also check the distance and angle between regions. The eyes should be a certain distance apart given the resolution of the image, and also they shouldn't be like 90 degrees. It should be like somewhere between 0 and 15 degrees, or like a reasonable angle between your eyes. Okay, and what I did there, I just like assigned bonus points for each favorable feature, and then at the end, the one that has the most bonus points ends up being the pair of eyes. Yeah. Okay, but this has some problems. I find the biggest problem is just the initial part of finding the eye candidates, because that varies a lot depending on like if you have glasses, what your eye color is. Like my current method of just looking for regions that are roughly blue, it doesn't always work well. So I got to find a better way to do that. And then the trade-off here is you want to have enough eye candidates initially that you don't miss the actual eyes. That's probably the most important part. But you can't risk having too many eye candidates. Because one problem, as you see here, combinatorial explosion. If you have way too many candidates, because you're checking things between each pair, that's going to be quadratic. So if you have a lot of candidates, it could potentially slow it down a lot. But also, if you pick up too many pixels initially, after you do some filtering, it might like combine regions. So then your eyes might meld with maybe your hair or something, and you don't have a nice eye-shaped region anymore. Yeah, so this is still work in progress. Okay, now Shane is up.
Now I'm going to talk about what I've been doing the last 2 or 3 weeks. If you would, can I stand over here? Yeah. All right. If you would like to ask questions or make suggestions, please don't hesitate to do so like while I'm talking, because then I can go a lot smoother if you do that. So for eye tracking, I've assumed that the eye is already located, kind of starting at the other end of the project and trying to work back in to meet Stephen. So what our original idea was to train a neural network to identify the gaze of the eye, which has already been done. 1993 paper is widely cited, has already used neural networks to track the eye. There are a few restrictions on that I'm going to talk about later. And we're going to use this information, obviously, to point a mouse around the screen. Process, step 1 is actually gathering the training set, basically making a huge set of images to use to train the neural network. Step 2 is to assume the eyes are located and crop them out. Build a network. Design pre- and post-processing methods. This is really important for neural networks. For the kind of data that you have coming out of the network and the kind of data that you're feeding into the network really matters when you're actually trying to train it. And step 5, obviously, train and test. So to gather the training set, basically I just had myself sit statically in front of a computer screen, and I had a mouse cursor go across the screen, taking pictures every few pixels, so you can get a nice variation of eye positions for each coordinate on the screen. That's a picture of my eye after it's been cropped out. Since I was fairly static, I knew where my eye was going to be, and it was fairly easy to crop that out. It's a low resolution image, which is required. You can't be feeding a 100 by 100 pixel image into a neural network. It would take forever to train. And this is network architecture. The input layer has the number of nodes equal to the image size. So if you have a 20 by 20 image, it's 400 nodes. The hidden layer is 16 to 20 nodes. That was suggested by the paper I was reading. This is what they had success with. I actually, during testing, we switched that around a lot from, I guess, upwards of 50 to 100 nodes down to 10 nodes. And the final, the output layer is 100 nodes, 50 for X inputs, 50 for X outputs, 50 for Y outputs. This allows a lot more control because you don't want to have just one node for X, one node for Y. It'd make it very difficult for the network to converge on a solution. You would also notice that the output layer and the input layer are separated. They're not fully connected. Pre-processing, basically I just took the image down to grayscale. Everything below 50 or so, I turned to black. Everything else turned to white so I could get major features of the eye. So it would basically have the eyelid, eyelashes, and pupil. And that it just rids the unnecessary noise that the neural network doesn't need. The input reshaped the image to a 1 by whatever the size of the image is vector to feed. So each pixel is fed to each node. Post-processing is used a Gaussian response vector. So since I'm using 50 nodes and the response is kind of very selective. So if you have, say, node 20 has the highest response, and in between any two nodes, you're going to have somewhat of 50 pixels of difference. So you want the response not to be centered around any one node, but actually be distributed across a few nodes on which it is centered. So here's a response to, it's about the X position of 500. You can see it's just below 20, I think it's like 19.4 or something. And that way it just allows much more accurate response for the network than doing just 2 nodes or doing one node and then another node is 50 pixels down, and it's not the quality of control that we want on the mouse. And so that was these were processed along with the images. So these were the actual like perfect training set. So the network would give an output, and then we would use this response to, I guess, calculate the error, and that's propagated back to the network so that it can learn. Training and testing did not go so well. There are several major problems which I'll talk about. Reasons. One of the major reasons, at least I think, after reading the paper very carefully, is that the original authors actually used specular reflection, which is basically they had a light source out in front of the face, and you can see the reflection right there. That gives a lot of information to the neural network. Basically, it can pick out where the reflection is compared to where the pupil is, and be able to differentiate positions from that. The network that I trained was very good at giving y-coordinate positions. Those would actually train, the error would be low, and it would be able to differentiate, mostly I think because of the movement of the eyelids up and down as I looked up and down. But the consequence of that, the very good y-direction training, the x-direction information was destroyed, because when the eye opens and closes, the pupil is occluded and you can't see it moving back and forth, things like that. Also, it might have been the case that the pupil moving back and forth was just not enough of a difference between each spot to train in the x direction. New directions, I'm going to try to use facial geometry. Basically, have 3 points, the eyes and the mouth, the center, or at least the center of the mouth. It could be changed up, but you're dealing with motion in several, I guess, dimensions. So you have back and forth like that, you have up and down, and then you have back and towards the camera. So to deal with this kind of motion, you have this length right here that will change depending on if your head is down, it'll be shorter. If your head is up, it'll be larger. As far as side-to-side motion, the difference in length between these two, I guess, lines, or the angle between the right eye and left eye. So you have this right eye and a kind of a perpendicular line going right there, and then this line going from each eye, and the angle right here could give some information about rotation. As far as the back and forth motion, still trying to figure that out. That's one of the more difficult problems to deal with. It might have something to do with considering the triangle as a whole and trying to get something out of that. And that's it.
Any questions? For you. Any questions? Any comments and suggestions to them? Help them.
Yes, help me, please.
Yes.
I think I have a question regarding how fast you can detect the face and the eyes. Like, usually, what image resolution do you need to process the?
Okay, so the original image from the webcam is 640 by 480. It does not work on that. I think I downsample it by a factor of 3. And then it works pretty quickly for that.
Okay, and then once you detect the eyes, when you say eye tracking, how your work is connected to Shane's like neural network training and testing?
Yeah, so it's connected because eventually we want to feed the eye images into the neural network. I mean, that was the original approach.
That was the original plan.
Yeah.
Obviously, that's not going to work.
But even with the facial geometry, I mean, you still need to be able to locate like the eye position in the center of the eye, so you can do whatever geometrical stuff you need to. So, like, what I'm trying to do is just quickly be able to find the center of the eye, I guess. So the first step in that, like, the reason we have face detection is just to narrow down the region to find the eyes, so you don't have like a bunch of eye candidates in the background or whatever. And then yeah, I'm still working on eye detection. But yeah, the goal is for it to work pretty quickly. So.
And for the eye tracking part, like what frame rate do you need to continuously track the motion of the eyes?
I don't think we've gotten to that part yet. I mean, we were trying to meet at we weren't actually dealing with eye motion, we were just taking static images of the eye. So it might be once he has the eye candidates down, we might rely on whatever he has. I don't know if we'd apply some kind of motion detection to take over. I mean, I think that'd be faster.
What do you expect, like one frame per second or 10 frames per second?
It works almost real time.
Yeah, I'm not sure how many frames per second. But I mean, if you're just moving in front of the webcam, it's like fairly real time.
Okay.
Maybe
I would say like
I don't know.
5 frames per second.
5 to 10 frames per second. I mean, it doesn't look stuttery. It looks like fairly smooth. So.
And do you know any like a commercial software that can do something similar to what you plan to do on this?
There was actually face detection software on the webcam, but it was bad, very bad.
Okay.
How
I'm
good
not sure.
the successful rate, the detection rate? I mean,
We haven't done any official tests, but we let a lot of people view it, and it's basically, it would follow your face around. There would be some problems, especially with white shirts, or if you put your hand in the range of the screen, it would pick up that instead.
Yeah,
Or-
I mean, there's still some background issues. Like in most cases, if you're moving around in front of the webcam, it follows your face fairly well. But like when I was wearing that red shirt, depending on my position, it sometimes caused problem. Occasionally, background things cause problems, so I'll need to do a little bit more work with that to make it completely accurate.
So you're focusing more on like, I guess Shane's like gaze tracking now, because you're finding the face and that's going well, but I mean, I guess you can't really
Yeah.
control the cursor with the eye, so is it more like you think people are just gonna like look around, kind of with eyes?
Well,
straight
that's
forward?
what I'm doing right now, like the actual head orientation tracking. Eye tracking is something I'm going to put on the table for a while, and do it if we get to it. If we're willing to put a light source in front of somebody and shine it in their face, I could try the neural network again, but that's really a restriction that we didn't want to do, because I mean, one of the problems with a lot of eye detection software that is actually out there is it's very cumbersome. Either you have to wear some kind of gear, or you have to bite into a plank. No, I'm not dissing yours. Or you have to bite into a plank and put your head on a headrest and sit there like this. So yeah, we're trying to keep it as simple as possible, just a webcam, nothing shining in your face, nothing like that.
anything else?
Yeah.
Have you considered using infrared at all?
No, not really.
I mean, yeah, I guess the original goal of our project was just to have you just have a webcam and it tracks your eyes, and no matter what you do in front of it. And then we realized, well, that's probably impossible.
It's
So
very hard.
We're trying
at
to make it
least.
so we have reasonable restrictions. Like instead of you can put your head like that, maybe you just have less freedom of movement, but it's still natural. So, yeah.
Do you think you'll be able to use Adrian in there, because they did the geometry of the face last, I guess, when Dimitri's presented they did geometry of the face for gaze tracking. Do you think you'll be able to kind of throw their code in to save you some time?
I'll have to look at it, because I basically just started with the geometry thing yesterday. So
'Cause they got pretty far in that. I don't think they did much with the actual being able to move things with it, but I think they got pretty far in the rule set for that. So you can look at it.
Okay.
I can give you that.
Your audience, I just have one suggestion. Yeah, I mean, just you can look at that. For example, you are going to be able to detect the eyes with some success, right? So one thing you can consider is keeping the pattern around that. You can allow for a few frames. Okay, so you have 100 frames. Okay, and you're doing what you're doing anyway. In the meantime, if you can detect, let's say, the eyes a good number of times, then you can crop that pattern and save it for the particular user. That pattern can be used to track the eyes again. So you get, because no matter how much you move, I tried it with mine last time. So I had several positions of my eyes located, and then, saved. And then no matter where I was, when I was checking the candidate, my eyes would have a good score.
Okay.
So even if I was rotated and so on, so because you can store several of those as you're right. So you can have dynamically, say, build a small database of eyes as you're detecting them. Sometimes you may store the wrong thing, but after a while you will see that there will be some outliers. You can eliminate them.
Okay.
Then that can help you with detecting the face even
Yeah, I mean, that's something I haven't really thought about yet, but I think
Right.
that would be really useful. Because
You
right
can try,
now,
you can try.
right now I'm
Something
just
like
looking at like
template
each
I know,
image
I know.
individually.
No, but you need
so-
your part anyway to be able to do that automatically. Otherwise, you will have
Yeah.
to click on it, and you don't want to do that. You want to have what you're doing. You detect where the face is, and after a few frames, automatically it's going to do that for you.
Right.
So if a new user sits down and in front of the camera, it's going to do that for him as well, or her as
Yeah.
well.
Yeah, I think that'd be useful.
Also one question, like the hue was like less than 0.1 or more than 0.9.
Yeah.
Do you know which scale corresponds to what?
Not really. That's just I
Okay.
took that from some paper.
Because you know, it's like usually it's within a range, and this time it's like the exact opposite. It's outside
Yeah,
of that range.
it's like- yeah.
So I was wondering. I haven't. Yeah.
But I think I didn't read too much about the color space, but it looked like it was a cylinder, so it might be adjacent anyway. I'm not sure about
I
that.
think actually the reason why this happens is because hue is a color thing. I just want to. It's more of like an angle related to an angle. So 0 is red. So 0.9 above 0.9, less than 0.1 is really around red.
Yeah. Okay.
That's what I think happens. Yeah. I
Okay.
just want to make sure because there's different ways to evaluate hue. So I
Okay.
think this one helps. Just anything else, anybody? No. Okay, now you do. Let's go. Do we need to see more?
Wanna go? Right, you need to go before, right?
Alright, you
You're going after us. So we're going.
Yeah.
Okay, so we're up.
Wait, anybody wants to use the?
They're after us. We're up. Yeah.
It's so much stuff.
Microsoft's trying to
Yeah.
use their
You want to take it back?
I think we can. They would have to
You
go up
first.
right now. We can't. Not unless they go up now.
How do you guys want to stand?
No, that's fine.
I didn't get a read.
Last time the only reason why I knew it was because of the last thing, last row. It was for like, I don't think professors were like.
Get another.
You like that?
Where do you click to go next?
Click the right, I assume.
Can we stand on this side or that side? Am I in the frame of the camera? Can I be seen in the camera? Whoa! It just moved, sorry.
Well, hello. My name is Ken,
And I'm Michael.
Christopher Stahl.
and our group is working on vehicle recognition and tracking using multiple video cameras. And so that's what we're going to talk about. Okay, we read many different research articles having to do with tracking different objects such as rigid cars, non-rigid people. And we looked at the different methods that they use for tracking the motion of whatever they were tracking. And some of them use color, blob, database matching, and so on. And they used either one camera, more than one camera, either live video or recorded video, different ways. Okay, our goal. So here's the thing. We looked at all the other research articles, and the difference between what we're attempting to do in our research is the difference between what we're doing and what they have already done is whenever they track something, they track the up and down and the side motions. Well, we're trying to record some video with a car that goes over a ramp, meaning that will make it a truly 3D tracking thing because of the height change and all that stuff. And that's our difference between what we're doing and what they have already done. And a very general description of what we have done so far. We track, the way we're tracking the vehicle is just we detect the blob which the vehicle would represent in the video recording, and then we find the outline of that, using that outline, finding the centroid, and then also using Kalman filter to make it track it in a better way, more efficiently. And Chris?
All right. The first section is detecting the vehicle. The first, we have 2 cameras set up we have pre-recorded video at the moment of our vehicle driving to, on the side and all around. I use background subtraction to get rid of the background so that, for the most part, the vehicle is the only object within the picture, which that allows you to use a blob detection algorithm. Because the vehicle is the only object in the picture, it obviously is the largest object in the picture. So once you have a blob of the vehicle, you can draw an outline around it, which lets you calculate the geometric center of it, which gives you a point on the vehicle in each frame from both the left and right camera. Now this is, on the left and the top right, you have the grayscale image of a frame, and then from there it's harder to see, but
Right.
yeah. You have, there is our vehicle after the detection, right there. The little blue dot is the center, and obviously everything else is subtracted out. And then if you go through these quickly, you can see the center tracks the vehicle over time and stays within the center of the block. So the next steps is we want to be able to have multiple points on the vehicle. I plan on using either circle detection and color detection, which will allow you to get the 3 wheels on each side of the particular vehicle we're using right now, and maybe the red base. And once we have particular points on the vehicle, we'll be able to use basic geometry to use that to transform it into a 3-dimensional plane and use information in math to get the actual real-world points.
All right, so he was talking about earlier, kind of give you guys an overview of how we're taking this video. You can see here that we have our 2 cameras that are set up, represented by the blue blobs, and you can see how their field of vision overlaps in that grayscale area. This is kind of how we want to show you guys we captured the video, so you kind of have an understanding of what our video frames are coming from. Another thing we mentioned is transforming our 2D points that we detect, especially the center right now, in the 3-dimensional plane. We're going to use this through these kind of set of equations you see right here, using just kind of basic geometry and what we know about the locations of our cameras. Since we have a known distance between them, and we know their focal length, or can use actually some of Dr. Chen's, one of his students has done some work on determining a focal length for uncalibrated cameras. We're going to hope to use some of her work to estimate the focal length, and then we know the distance as well, so we can set up a system of equations in order to determine the real-life parameters about the x, y, and z directions in order to transfer our 2D images into a 3D model, which we can later plug into the Kalman filter, which is what I've been working on. Kind of a brief overview of what the Kalman filter is. It's basically an equation, or a set of equations with an input vector of measurements. In the case I've been working on mainly is velocity and position, because that's the information we're going to be feeding from my 2 associates' work. And so you feed in a vector of velocities and positions and the x, y, and z axis, and you get out where the predicted true value is. The reason you use a Kalman filter is because a lot of times your measurements aren't exactly accurate. If you say a vehicle is at a certain point in space, it isn't necessarily there due to several reasons. Either you measured wrong, or your measuring instrument is not very accurate, or just kind of general error from the whole process. The Kalman filter is actually extremely important. It has been a great development because it helps minimize the mean square error, which means it's a lot better than just taking the average of a bunch of guesses of your observation and then claiming that is where your point is actually located. And really how it works is it utilizes a combination of a model, so you kind of have to have an idea already of how your object is going to be traveling. So you have to be able to plug that in, and then also you have the observations that you take from the outside world, and you can kind of compare what your predicted value is and what your observed value is, and then calculate where you think your object is actually going to end up. So that's basically what I've been working on implementing thus far. To date, I've actually got a linear Kalman filter working, which means it's just a very simple set of linear equations. Basically, I've been tracking a 3-dimensional cube on like a 1 by 1 by 1 line. I'll show you a picture of that in a little bit. I actually track each dimension separately, so that allows me to adjust the error accordingly. I imagine that once we actually get information from the tracking of the truck, our z direction is going to have a lot more error to it, since we're only estimating the amount of z direction movement. We don't actually have any way we can measure it directly from the images, unlike the x and y direction. So here's kind of a picture of what I was talking about. You can see the purple lines represent each one of the 8 points of the cube, so you can see how it kind of moves just in a general linear motion. From here, I actually plan to do a lot of changes to the Kalman filter. That's kind of my major focus at this point. It's actually turning it from a linear system into a nonlinear system. That's our final observation of our vehicle. Is actually not going to be linear. It's not going to move in a straight line. It's going to move up, down, left, right. It's going to make turns. It's going to stop. In order to do this, we need to approximate a linear system, or take our nonlinear system and then use the Kalman filter to approximate a linear system. We also need to tune our air parameters and inputs. Since right now I'm just using a lot of synthetic data, obviously you saw the simple rectangle moving in a 1 by 1 by 1 every square. It's pretty easy to predict and know where it's going to be, but in the real world we're not really going to know what our exact air parameters are going to be. I can't generate the data. So once we actually get it all up and running, we're going to actually have to run a couple tests and actually get down on the floor, measure how far the car has moved, and then compare and see what our outputs are, so we can kind of fine tune this to make it as accurate as possible. And kind of finally what that's called is the extended Kalman filter. Once we get all of that together, our hope is we kind of pull our both ends of the project together, the vehicle detection and the points, feed it into the Kalman filter to track the vehicle. We kind of have multiple avenues which we want to explore. The first one is actually estimate the velocity. This is pretty easy to do since it's kind of built into the program already. It's just not something we're monitoring. Basically, since you have the vehicle in frame 1 and frame 2 and you know the elapsed time, you can just subtract the distance once you actually have those distances and figure out the velocity. Another idea we had was actually to estimate acceleration. This might actually turn out to not be feasible because it can accelerate. We don't know if there will be constant acceleration or non-constant acceleration. We have to have a lot better idea, and it's got to be a lot stricter parameters if we are going to do this at all. But this is something we at least want to try and keep in mind if it is, something we can at least try out. We also want to maybe turn to the avenue of detecting multiple vehicles. This would be useful if you're in traffic in the real world situation where we're using this kind of system with 2 cameras on the front of your car or on the back. You don't just have a car in front of the lane, in the lane in front of you, you also have it in the lane next to you or in the lane to the far to your right or behind you. Finally, we could detect possible collisions. This is another difficult thing, kind of spinning up our research of the satellite detecting group. Maybe we can see if there's a car ahead of you and their velocity is slowing and your velocity is increasing, and we know you're on a trajectory to hit each other. Maybe we can give some sort of warning, or even if we can't detect a possible collision, possibly detect a collision after the fact to alert emergency responders that there was an accident at this location. All right, are there any questions?
You went too fast, didn't you?
I went too fast.
That's why you don't have 25 minutes. Any comments? No? You're not going to help them? Yeah? You're trying to help them? Oops, I broke it.
Nothing.
Really? Okay.
All right.
How did you do the background elimination part of it?
The background, it's a mean filter, and it takes all the images, and because there's an object moving, it detects that change within every, and then so it basically deletes all of the change that is constant.
So did you collect the video file with that moving vehicle that you show in the presentation slide?
Yes, that's our video.
And like how fast does that vehicle move?
With MATLAB, the way I have it set up, that runs pretty slow because like the top 2 videos you don't really need going, but I like watching everything at once, so when you start running 4 vehicles and 4 movies in MATLAB, it slows it down a lot.
But this picture does show the stereo camera, like 2 cameras.
Those are the 2 separate. That's the left and that's the right camera.
Okay.
Yes.
The top left image is our actual image from our left-hand camera in grayscale, and then the one image below it is once he's done the background subtraction and added the centroid to it. And the same thing for the right side.
Yeah.
No questions?
Not for me. No, just suggestion. I would say just narrow down your goals at the end.
No down our goals again.
Yes.
Well, those, I guess I should expand upon that, kind of say those aren't necessarily what
I
we
know.
want to do at the end of the project, but rather, once we pull our parts together, directions we could pursue.
Right.
So just kind of general ideas.
Maybe I have one comment, the background a little bit, contrast, the text contrast is not clear to read, a little bit, at some pages.
What's that?
The
I submit
gray.
is the PowerPoint slides.
Yeah,
Oh,
yeah,
background.
because the lighting condition.
Yeah, the lights,
is-
yeah, right,
is
yeah.
function, yeah.
I think it's gonna be better if it was like, the lights were off, but yes, they're not. No, because if you look at it in the actual presentation I saw yesterday, I mean, you could see the red outline and everything, that just not show.
Yeah.
I know there is a red outline.
Yeah, there is a red
I
outline
know,
there.
I've seen it, so,
You can.
no, that's good, that's good.
No one else?
No? Okay. So did any useful information that
No, but some ideas of things we might do,
you get new students?
but everything.
Everything requires money.
But I think a lot of school, Scott is really willing to do it. There was a big show, right? The crowd was like, no, Jim was there.
Already, I don't understand. And you don't ask for it, so.
Another.
Did he ask you? No. Did he ask you?
Said, why, want to say no?
Hey, I'm Anise Udiani, working with Aliana and Purin, and our project is sensor management for satellite collision alert. And it's basically the overview, why we tracking, why we interested in sensor management for satellite collision. Well, because due to the increase in launching of satellites, the outer space has been increasingly crowded. So basically, we're looking for an efficient way to track and detect collisions before they happen. Due to sudden change in velocities and the trajectories of these space objects, we need to develop a efficient way to track these satellite collisions before they happen. The sensor management part is basically we need a realistic model to control and manage the sensors that detect these satellites. One of our goals is to determine the best time to observe when each object gains to determine the best time to observe the maximum amount of information dealing with the collision event before it happens. Schedule the sensing actions for various space objects.
This is our system model. It consists of two LEOs which contain the sensor on their board, and 4 GEOs. We decided to start with just 4 GEOs, for space objects to track from 2 GEO. This is we modeled it in 3D, so you can see you can see here 2 LEO which are closer to the Earth surface, and 4 GEOs. These are 2 actually. They are very close to each other. This you can see here. First, before we can take the measurement, we have to take into account the orbit of the object we are tracking. Here you can see the 6 elements of the space object we are tracking. For example, we have the inclination angle, we have right ascension of ascending node. This is the ascension tree, which actually points out to perigee. Perigee is the closest point between of the orbit to the Earth, and this is the line of nodes. This is the actual intersection between equatorial plane and the orbit plane. And in our modeling, we will have to translate these 6 elements for the to the XYZ system of coordinates. Because we have different kind of sensor of different LEOs, actually all of them they will give us just four measurements. The range, which represents the target position. This is this one. The azimuth, which actually is an angle, what is counterclockwise from the inertial axis to the projection of a target on the elliptical. Sorry, it's actual. If we project it here, it's gonna be like this way. The elevation angle, it's going to be the angle from the projection of the target on the inertial xy plane. It's going to be this one from here till here. Like it's going to be like more like inclination. And the range rate, it's just the speed with which the target position is changing.
Basically, this is some of the constraints we had to take into consideration when trying to develop a realistic algorithm to manage the sensor. The dynamic sensor management of heterogeneous and distributed sensors for space tracking is theoretically challenging as well as practically. So one problem is the sensors have a finite slew rate, which limits the how fast the sensors can turn to actually capture the satellite. Another constraint is the physical and environmental tasking of the space platforms, including jitter, the relatively slow speed, the limited operational range before exhaustion of power, and communication dropouts due to like a loss of signal in outer space. Another thing we had to take into consideration is that the sensor should categorize information in order of importance, which means basically if the sensor gets a reading of 2 different satellites, and one is maybe for instance is just a residential satellite, and another one is say a military or something of importance, then the military satellite should be categorized as more important than the other one. The sensor should be able to operate in real time, despite the presence of true or false targets. This in the case of debris and other which could be considered false targets. So the sensor should be able to operate despite the presence of those. It should account for limitation associated with resolution and sensor noise and the physical extent and shape of fields, false alarm characteristics, and clutter characteristics. Radar, optical, and infrared sensors have different characteristics and strengths. So basically, when implementing an algorithm, we would have to take into account the fact that in one scenario, the radar could have a stronger range detection than the optical sensor, and in a different scenario, vice versa. So next, the sensor should be taxed such that it's in the right position and tracks the satellite at the right time.
So I'll talk about the satellite tracking part, and this is what I've done so far. First, our system is set up in the Earth-centered inertial coordinate system, and in this system, the x-axis points to the vernal equinox of the Earth, and the z-axis points upward to the North Pole, I think, and the y-axis finishes the right-hand coordinate system. And all the space object that orbits around the Earth follows this equation here. That's the motion equation, Keplerian motion equation, and in this equation, the r here is the target position relative to the center of the Earth, and mu is just the gravitational constant of the Earth, which is given, and the object velocity and the radial velocity is given by these two equations. And based on those information, we can write the state propagation model of the target system, the target satellite, I think. It's given by the x prime, it's fx plus w. The fx here is first the x here is just the xyz coordinates of the target, and the vx, vy, vz, the velocities along each axis. And the fx, which I think is just the derivative of xt, and w is just some additive noise to the system. And the satellite data can be obtained from SpaceTrack, and the data is given in the two-line elements format. And basically, what that contains is the orbital inclination and all that we just mentioned. And first, we need to pass the TLE data to a propagator that generates the true trajectories of the satellite. And we use the SGP4 and SDP4 propagator here. And basically, this is developed by the NASA and NORAD, and it is a more realistic model than the one that they used previously. I think previously they just used the Keplerian model. But this one is more realistic because it actually considers other factors that affect the orbit of the satellites. For example, the radiation and the gravitation force of the moon, etc. And what we get out from this propagator is the position and the velocities, x, y, z's, and the v's. And for right now, the measurement model that we use is a very simplified model, and we assume it can always obtain measurements about the satellite whenever the Earth is not blocking the line of sight. But this needs to be improved later. Right, this is just the measurements from the sensing satellites. The DR here is the range, and DA is the azimuth, and the elevation, and the range rate. Basically, these just corresponds to what we mentioned at the beginning in the sensor measurement part. And how do we determine if the Earth is blocking the line of sight? Basically, we have this equation, and if there exists a route between like 0 and 1, such that the value of this equation is smaller than the radius of the Earth, then the measurement from this observer is not available. So the Earth is blocking at this time. And after we got those, then we first just define error covariance matrices. These values is predefined, and we might need to tune them later. And we pass the initial states, that's the x, y, z's, and the velocities, to an unscented Kalman filter to predict the next states. And if the measurements from the sensor is available, then we use that to update the prediction. And if not available, it just predict again, I think. So this is a visualization. You see the Earth is in the middle. They got 2 points here. That's the LEO satellite, which are the sensors. And the 4 GEO satellites are orbiting around. It's being tracked. You might not be able to see here, but the blue star at the in the middle is that's the estimated position, and the square block is the true states. It's a true position, and it just propagates like this. And Leona will continue.
Here you can see the error we are getting when we are trying to use our unscented filter based on measurements we are getting from our model. So you can see at the beginning, once we start propagating the states and taking the estimated values, we can see that the difference between true state and the true position what we are getting from when we are generating the orbit, we get the true state of the satellite, and when we just get the initial position and using an unscented filter to estimate it, we can see the error we are getting. So at the beginning, this is the value in kilometers, and this is the time track. It's like it's 1,000 minutes. So at the beginning, our error of estimation are very high. Once we are getting closer to like 200 minutes, we get the error. It's like it's going like down, and this it could be because of the earth blockage, because we cannot use the measurement value to update our estimated value. For this reason, our error is very high. Once we get to get the measurements, because we take actually right now we are taking measurement every minute, we can see that error is closer to zero. And this is our next steps. Once we created our 3D model with 2 Leon for geo, we are using an unscented Kalman filter just to create an estimation and see how, just to predict the state of our satellites. Now we will work on actual management of sensor management system. First of all, we will have to develop a more realistic measurement model. We know that we have a limited range of view because of the earth blockage, and we know that our sensor will take some time to maneuver from one position to another because we are inclined in one direction, so we will have to choose which geo to track. Another point what we have to do is improve the collision alert algorithm. I just tried yesterday their last year group collision alert algorithm, and I put for our geo because we use the real geo's data. This data gave us a probability of 0, so we will have to change the orbit of our geo. We will have to find a way to change their inclination, and all these 6 elements we will have to change them to obtain a possible collision. Last year we did it by moving in opposite direction. I did the same way and it worked. For example, I put first two geo that one it's in one direction, another it's another one direction with the same data, and I got the same results like they got. So we will try to use the algorithm, and also we are going to take into account the velocity, because if we are speaking about space object, it's not just moving, it's not just his position, it depends how fast it moves. Some of them move faster, so the probability that they will collide it's higher, with like it's in time. Once it will take less time to collide, so we have to take this in account. And also we will have to take into account the sensor scheduling. Now we will have to categorize our satellites. We found out from the paper that the measurement of satellites is actually every 50 minutes. So we will have to categorize which satellites are more important to take the measurement from, and which are not. For example, which have a probability of collision like 30%, we need more, we have to pay more attention to them than to those who have like 0% of collision. So we will have to categorize in first group, second, and third, depends on the probability. Also, we will have to take dynamic measurement interval. We will have to know how long it takes for our sensor on our LEO to change its direction of satellite, which geo he is gonna, for example, if it's directing this way, he's taking measurement from this satellite. It's gonna take like depends how long it's gonna take until he will be able to rotate this way and take the measurement from this, and we will have to take into account this one because the timing we will have to decide which target we will want to track, and we have to take into account how long it takes for our LEO to move from one place to another, and to decide which one to track. It's just our, like, once we did already the 3D propagation, or like we know which, because we already did the 3D model of our system, we used unscented filter, we created all, now we will just work on our management system of this space objects.
Any questions?
Well, if you go back to the plot, I think it took about 200 minutes to get a relatively good estimate. No, the last plot, your error.
Three
How,
slides.
how often are you updating?
Every 60 seconds, every minute.
Every minute, and it still takes 200 minutes?
Yes, we are like we used the last year, like we didn't want to give attention too much to the filtering part. We are just using their information from last year, so we understand the actual model. Like it took us a lot of time to understand the actual model. So we are going to use their work and start doing right now the sensor management. So we created our 4 geos. We will try right now to change the inclination. We actually won't care about it. We know that it creates big errors. We just will try to work.
No, actually, we changed something from their previous work. Actually, originally they just used the coupling model to predict the true states, but we changed it to SGP4 and SDP4.
For LEOs.
So there might be some issues with that.
So related to that, do I understand correctly that your sensors are on the low orbit and you're trying to track geo ones?
Geo.
Okay, so you assume that this orbit is always perfect and you're trying to...
But we assume the LEO is, we know
Right.
this.
Right.
Yeah.
Okay, you know exactly, so you expect these to wiggle, but this one not.
Right, actually, we're just tracking the geo. The LEO is fixed, I think.
Okay.
Right.
Any other questions?
Like,
Come on.
When you plot this, basically, finally, what's the actual error for these both geosatellites you track? I think they are
The final part?
yeah, the final part is done within 1
Assume
kilometer or 10
that it's
kilometers.
about like less than 5.
About 5
Less than
kilometers.
5.
Less than 5 kilometers. And you said that you already use the SDP4 propagator instead of just the controller. Okay.
What's your error measurement in? Is it meters or kilometers?
kilometer.
So is that an error of 6 kilometers useful? I mean, I'm just curious, because satellites, I mean, they're...
It actually, I don't think it's like, the problem is that it's a blockage of the air, so we have to we find another way to deal with it. Because once it's blockaded by the air, you don't know, so for this reason you have big error, you don't know how you're gonna, like, we have to, like, to deal with it, we have to find a way to update our information so we don't get so big errors.
I'm talking about more at the end, not at the beginning of your...
At the end,
final
5
error.
kilometers is not so much.
I mean, that's enough for it to be effective to worry about collisions and everything?
5 kilometers is not much. Like even if you have an estimation, you will take into account what is the distance minimum between them. So I'm gonna put what is the distance between those 2 satellites, because we are dealing with, we don't take into account the whole object. We are taking just the point, the tracking point of the object. So we are gonna put a distance between those tracking points, and it's gonna be, I think, bigger than 5 kilometers. You know?
Yeah, well, I guess the question is still whether, like, the position error by 5 kilometers in tracking geosatellite will be good enough for collision alert systems, right? And right now, I think it's still based on some unrealistic sensor models that we're working on that. So it's hard to say, but if you think about just the Earth ablation effect, so-called J2 factor can give you the position error down above 15 kilometers, right? That's what they already did, just to see the difference between the Kaplan orbit and the SGP4 propagator, which I think takes those kind of issues into consideration. The difference is by around what?
On average, it's about 15
On average, about 15 kilometers.
About the sensor management, I mean, any ideas? I mean, for example, let's say you have one important satellite and one not so important. I mean, how would the scheduling work? Like you track the most important more frequently?
Yes, it's gonna like
I think
15
it's based on the collision probability, I think. If the higher the probability, the more frequent we measure.
Okay.
Well, again, there are different issues to be considered.
Right.
One is like, yes, collision alert, like how likely two satellites will collide, or maybe one satellite will collide to another space debris. And another issue is when they're going to collide, how long does it take?
Right.
And also depending on whether you have available sensors to monitor those things.
Yes, it's gonna, we will have to
Because
take
sensor
an
management is like you need to plan in the future to see if something happens, whether you have any way to closely monitor that.
Hey, I still have that certificate in my office. The robotics, they don't know, there's some.
He's willing to demonstrate.
He's the sensor.
You just press up and down.
Alright, we can all come back down to earth now. And
I have
pre-
a single
I don't know.
what are we waiting for?
No, I mean,
We are good to go.
Okay.
Oh, he says we're good to go. Alright. So ours is a lot like the first groups. We are doing, well, a little different though. We're doing pupil tracking, and we're trying to apply it to mouse control for, say, quadriplegics or Lou Gehrig's disease, people that, or, you know, if you just want to have fun or something. Alright, so any past research done, we're using an optical camera, and it seems like everybody else took the more lazy route and decided to use infrared, which infrared is really good because you can have a bright pupil or a dark pupil technique, which makes, and it almost pretty much eliminates the glare except for the LEDs. So it reduces a lot of background noise or anything like that. And let's see, another past research done is, did they ever use high resolution cameras?
No. It's always like low resolution cameras.
Yeah. So everybody also used a low resolution camera, which is very bad if you like, you know, most cameras now on every laptop they have one built into the monitor. I mean, and actually from that distance, the pupil is kind of small. It's kind of hard to actually see the difference. So I'll get to why we have the hat here. And see, other approaches that they did was the Hoff transform and edge detection, which I don't know in C, but whenever we did it in MATLAB, it is quite slow. Maybe, I mean, less than a frame per second, which is very impractical because, I mean, a person's going to want to move the mouse a little faster than that. All right. So our equipment, this is what we were given, or we went out and bought.
I heard something that don't. That's what we were given. So, okay, yes.
I say thankfully we were given that one because I couldn't afford that one by myself. And we were given one webcam, a Logitech Pro 9000. We were given, well, I've rescued a baseball cap. We when our local Radio Shack supplied us with some nylon zip ties for an outrageous price.
He's very detailed.
We got a wonderful pair of glasses from Dr. Demetrios and some electric tape. I don't know where you got that.
I think you bought it.
Yeah, but
You paid for it.
Yes, we paid for it. Ghost typing. All right. Our first prototype, which is not this, was the glasses. It had the lens removed, and we simply taped the webcam right onto the glasses. This did not work well, because to use it, you had to actually have your hand up and holding the glasses, because if you leaned forward, they'd just fall out and bang onto the keyboard. It's terrible. And the glasses moved a lot. I mean, anybody that wears glasses, you're constantly probably pushing them back. Like he just did it, pushing them back onto your face. So it's really hard to get a constant picture of the pupil that stays frame to frame. So this is our second prototype. I think it's a lot better. We have the webcam fixed right into. We made 2 incisions with just a plain knife right into the bill of the hat. Use zip ties to tie it down. And this is a lot better because unless you wear your hat very odd, I mean most people put it on their head and that's about it, and you'll get a steady picture. It's not going to move around. It's not going to fall off your head for some reason unless you're using it upside down. And it also produces shade from the overhead lights. So the only glare you actually have is coming from the monitor. So that we can deal with. I mean, that's only one source. We'll try to fix that. All right. And take
I have the laser
you want your clicker?
So we're going to talk about the image processing steps we applied to the images after we got them from the webcam. So right here is the normal image that we got from the webcam after it's turned into black and white. And over here is after a threshold is applied where only dark values remain. See the dark from the pupil over there remains. Now the reason why there's a hole right here is because right there's a glare from the computer monitor and you can kind of make it out from a distance. So yeah, that's what I talked about. And also this depends on lighting conditions too. Like we eliminated the factor of the overhead lights, which were pretty bad too, but we still have like windows, we still have like monitors and stuff like that. Okay, so the second step we did was, this is the image from before, after the threshold is applied. We took and applied a median filter to that image. It was about like 17 by 17 to remove all the noise up here. So these are basically eyelashes up here. So that smoothed it out a little bit, and that made us a little bit more happy with what we got. Then the first computer vision step we did was we did region growing with MATLAB's BW label. Then we detected the centroids and found the area using region props. And the last step we did area thresholding. So in other words, for area thresholding, we took the area of all these blobs right here, right here, right here, all those, and we took out the small ones below a certain threshold that we predetermined. And we wound up with this image right here, which is just the pupil now. And once we have all the image processing done, there's a few options we developed to try to find the exact right center of the pupil. The first one we did was not so good, and all it did was it found the largest blob. It's going to be most likely the pupil. The advantage to this is that it's very fast. You know, there's almost no processing that has to be done on top of what we've already done with the image processing. Disadvantage is it might not be the pupil. You know, it could be, if you close your eyes, it could be the line of your eyelashes and stuff like that. And as with before, glare is still a major problem with all these techniques. So this is the size algorithm. See how there's one smaller one right here, and then a larger one right here, and it would find it right. I don't know.
Our red dot disappeared.
Yeah. Did you do that in PowerPoint?
What? Yeah, it was supposed to be in there.
Well, there was a red dot like, in the middle there.
It would find the centroid of the.
I think it's there. It's just that the.
Yeah, because for us it didn't work.
Yeah, it's very bright.
Good way.
Yeah, the
Here's the light.
Well, that may just affect a little bit on the video recording.
We'll just point out.
Yeah. So there is supposed to be a centroid right here.
But it would be kind of.
Yeah. And the next algorithm we tried to use was radial expansion, which is basically we started the centroid that region props provided us,
and then we moved out along the vertical, the horizontal, and the diagonal axes. And you go until you find a change. Basically, you find the edge of the BW image that we saw earlier. And then it would calculate a candidate score for all the centroids, and the candidate score is defined as the summation of each radius minus the average of all the radii. And the closer that is to 0, the more circular it's going to be. In a perfect circle, all the radius should be the same, so the average, the radius minus the average would be 0. So we look for the smallest one and consider that to be the pupil, just based off of simple shape detection. Now the disadvantages for this are, other blobs may be more circular than the pupil, especially if we don't take size into account. And also, there's no accommodation for glare, just like all the other algorithms. Okay.
Once again, we have no doubt.
Yeah. So there's supposed to be a dot here.
Can you see it? If you can see it, you can point at it. Can you though?
No, it's not showing up well. I think it's a problem with the lamp, probably.
Yeah, I think so.
Yeah.
All right.
I get this. All right. So.
Might be the projector because it looks too blue. Maybe the projector doesn't display anything red.
The projector hates this.
You're going to get the red glow before we do this.
Yeah, we were supposed to have
No red.
We have no red. Should have used red font. So this is our latest method for finding, which is edge detection. Now, we're not using any of the built-in edge detection in MATLAB, so we'll get around some of that processing time. All right, so what it's going to do is, maybe I should draw a picture. That would be the best. Or do we have
Put the hat down, draw a picture.
Drop the hat and draw a picture?
You can do that.
Or do we have one? Oh, yeah, actually we have one. So what it's going to do is it's going to, after all the threshold and everything, it's going to draw these edges right here. You see? No, we don't have red dots.
Yeah, the red
anymore.
dot's supposed to be right here.
Yeah, there'd be, and then what it's going to do is it's going to find the largest diameter between the two edges. So right here, it would find this distance right here. That would be the largest. And it's going to plot the center. Now, however, there's some disadvantages to this. Now here's where I can draw a picture. Let's do this one. Now, even after the thresholding, if we have something that looks like that as the pupil, and say for some reason we have a blob out here, well, that's not going to work very well because now it's probably going to find this distance right here and say the center's right there. So now your eyelash is your pupil or something like that. So that's a problem we are working on right now. I think we have the solution, but we're not quite there yet.
Yeah.
It's still working.
The area thresholding would help with that.
That's why we're going to get to combining our methods, which should get rid of that. All right. Let's see. Here's a good picture. It actually plotted it, I think, right in the center with this. Even with the glare right there, it still was able to find. And that's how we're going to probably get around the glare problem. All right. You want to talk about putting it all together?
Sure. So we're still going to do all the same image processing steps we presented to you. And then we're going to find the large blobs like we did before. We probably aren't going to use the shape detection because that was kind of slow. I mean, it could be improved, but it seems like the edge detection is the best method for finding the exact center of the pupil. And yeah, so let's see what else.
Oh, we got mouse control. So that was a quick hybrid.
Let me talk about performance runtime
Okay, go
for a
ahead.
second.
Because
yeah, you're probably going to ask anyway, so I should talk about it. So the first method we presented was the
large blob.
Yeah, the largest blob
That was
one.
quick.
And that one runs perfectly, no problem at all. The second one we did was
Perfectly, you mean real time?
Yeah, like
Yeah,
I
real
mean,
time.
All
you-
frames processed
Yes.
with
You're moving your eye and the red blob's just going along.
that had our best results so far. The circular method is like 2 frames, maybe 5 frames a second on a good day. And then the last one is probably going to be around like 10 frames per second.
That's what we're aiming for.
Yeah.
So if we can get all this to work, if we can put it together in our hat works wonderfully, then we'll try to control the mouse. So what we're going to use a GUI system that has the user. We have 4 boxes for your 4 corners of the screen. You click the box, you look at it, and for about, is it 5 seconds or 5 frames? Or, I think it's 5 seconds.
It's 5 seconds.
So 5 seconds for whatever frame rate we have. It takes averages for that location. And it spits that out as that is the point at the top right when the user's looking at it. So it gets those 4 points, and it makes some type of polygon from that. So it's probably going to look like something like a trapezoid. The problem is your monitor is not a trapezoid or some type of skewed rectangle. So we had to find some way to transform it so that when a user is actually looking towards the top right of the screen, the mouse will actually move to that point. And here's a good picture of it. And no more red points again. So like this would be the person looking at the top right, bottom, or top left, bottom left, and whatever. And using the transform information, you can see how it stretches the image in the proper way to create a square. So yeah, it kind of looks funky. So now when the user looks in the middle of the screen, the transformed point will tell the mouse to go to the middle. And that's what we're hoping it will work like.
Yeah, basically what that's going to do is it's going to get scalar value and it's going to scale the points. We aren't actually going to do this image transformation.
Well, yeah, and another thing, we're going to have the program get the screen size of the monitor, whatever resolution it's at, and you have the image resolution, and all it should be is just multiplying it by some type of scale. So if like the pupil's at 50/50 or some point like that, maybe on the monitor that would be 1,000, 1,200 or something like that. I don't know. Any questions?
Have you thought all how you're going to deal with movement? Or are they going to have to? Are they going to have to stay fairly like static, or are they going to?
Well, that's the thing. Like with this method, it should transform it for like either if you're on the side of it, that would skew the polygon in some way, but it should transform it back into a square that the point should go where it's supposed to.
He's talking about like moving your head though, and in which case you would have to recalibrate. That was going to be our second part of the project, but since time is winding down, I don't know how much we're going to get done with that.
I mean, what matters is just the relative position of the camera to the eye. So I can move all I want as long as the hat stays exactly in the same place, right?
Yeah, but your pupil will move different positions based off of where you are. I mean, if you move like from here to here, you will not have a big difference in where your pupil is looking.
Yes. Okay.
Also, it's probably also a problem with what we're doing is some people will maybe look half the direction and then the other half of the direction or whatever the distance will be moved by the pupil. So if I want to look at Dr. Mitros right here, maybe I'll move my head to the seat and then my eyes will look at him or something like that. So actually our method doesn't account for something like that. So hopefully they'll be staying still.
Yeah, this is okay. This could be a component of a bigger.
Yeah.
We can only work on a certain aspects of the project, not everything. So you can't. The amount of time to everything. So that's fine.
Anything else?
Any other?
Do you guys anticipate a lot of slowdown when you're going to use that combination? You said you were almost real time with one of your methods, but you're down to 2 or 5 or 10 frames with a different one.
Well,
so if you put it all together, do you imagine it's going to slow it down even more?
Close to real time.
Hopefully.
Yes.
But
first or second is pretty good.
We eliminated the step that was taking the most time, which was the finding the circle, because it would have to go pixel by pixel on all the radiuses, and it took a lot of time. But the large blob thing and our own little edge detection method, it's fast enough.
Also, probably some of the things you do in the different methods are common. For example, the DW label thing is more or less common, even if you try to take the size or even if you want to take the edges. So that's a common part. So it's not going to be like you add the times of all 3 methods together. It's probably going to be.
I was just wondering how when you combine them together, if there would be.
But it would probably be slow again. So yes, you have to see.
Worst case scenario, they might have to wait for the mouse to get there. But it'll get there.
And eventually, how sensitive do you expect to move the mouse like among different regions? You want like 4 different regions, you just use the pupil to control that, or maybe more than that?
That's really depends on the resolution that we can get the camera to, because if you only have a 100 by 100 picture of the pupil, you know, even if the person's going from one extreme to another, and you have 1280 across pixels, then like a change of 20 could be, you know, it would be you won't be able to go like from maybe one icon to another, but maybe you'll be able to get the other icon.
Usually, which side is more sensitive, like more left and right or up and down? Usually?
Up and down seems to be a little worse than side to side.
Okay.
Comments?
Suggestions, please?
Get the red bulb fixed.
Yeah,
Yeah, there.
I like that.
There's something wrong with the projector, bro. No comments? No?
Nope.
Question? Already answered my question. Anybody else? No? Thank you.
They don't want us to finish this. That's what it is.
Yeah, you just want to stay here.
Yeah.
I mean, we can do that if you really. I think the other people want to present.
Oh, okay.
All right.
I don't think take my going seriously, right? Some of them I hope you do. That's all I'm doing.
I like that.
Am I supposed to wait for a second? All right. Good afternoon, everybody. Our project is about. Hi, Dr. Green. Our project is about the traffic monitoring using video sequence, and our team members is Michael Giordino and myself, Firas Quran. Okay, past work was done by Michael and Brandon Samuels from last year, which included background subtraction, vehicle identification, edge detection, acquiring center locations, similarity-based identification, and history-based size estimation. And the present work done by both of us is code division into multiple functions, which is just separating the code, the previous old code, into functions to make it cleaner and more efficient, and identifying between new vehicles and lost vehicles, multiple vehicle detection per frame. I'll talk about that later on, and Michael will talk about directional adaptive window size and region-based image processing, and improvement of neural networks. Well, before beginning, the steps performed before was the creation of a background image and background subtraction and threshold and enhancement. This was talked about in previous presentations, and edge detection and identification incentives. So, okay, we have a problem that our program couldn't identify between new vehicles and lost vehicles. And you would say, why? Well, why is that a problem? Well, it's a problem because the search window, which is the tracking window, would stop looking for the vehicle. Like, for example, if the vehicle went behind a tree, it would stop tracking it. It would just disappear. And once that vehicle, the same vehicle, came out behind the tree, then the search window would directly just go to it. It's not really tracking it, but just placing a window over it each frame, which was really not tracking. So the solution to that is we defined everything within the frame, which was 480 by 640, to be out the vehicle out, which didn't include, and everything else was always lost. Now the meaning of lost right here is that each time the search window is on it, it would always track it, no matter what. If it's within the coordinates of the frame, it would keep tracking. So this fixed the problem of identifying between new vehicles and lost vehicles. And the second thing is the multiple vehicle detection per frame. Over here is we wanted to track multiple vehicles in the same frame. So what we did is we had to make sure that it would identify between new and old vehicles, new and lost vehicles, and place the search window over it and keep always tracking it frame by frame. And if it goes behind a tree, the window would extend and search for the vehicle and wait till it gets there and tracks it. And over here, this is an output. You have 4 cars, 4 vehicles, and this is frame 233. The first couple of frames, it starts I think at 200. The first couple of frames doesn't count because everything is new. So I took it from frame 233. You can see there's 4 frames, 4 vehicles, and it says that all of them are lost, which is what we want because we always want the search windows to track the cars at all times, and it tells you how many of them is new. Now, it's important to know how many are new because it extends the dynamic array of the for loop, and it adds another new window, so we know how many vehicles there is. And here at frame 238, which is 5 frames later, you can see this car previously was, see, it was behind, before the tree, and now it's after the tree. Now that same window extended and actually caught it over there. And it's supposed to show a new vehicle right here, but because it actually did, but because this is frame 238, it says, okay, there's no new vehicle, so don't extend the dynamic for loop by 1, and don't add any additional search windows in the frame. And over here is a video.
Click on it.
Yeah, please click on it. You can see there's a vehicle right there. It loses it and it predicts that's going down. That's a problem we got to fix. You can see that window searching for it. It's supposed to move this way because that's the predicted path for that car, but that's a little problem. You can also see that here there's some noise, so it thinks this is a car right here. We eliminated a lot of the noise, but we still have problems. And, huh?
No, I said there's a tree moving. There were about 10, 20 of them there before. So
Yeah, there's more.
It was really blowing.
And we use neural network to improve that. Michael will explain later. If you could start the video again, I want to tell him something. No, actually, stop. Yeah. Start it again.
Okay.
If you look at that vehicle right there, it loses it behind it. If it still thinks it's not a new car, it's still searching for it because it's within the frame, like it's within the 640 by 480 frame. So it thinks it's actually still in the frame, but it's not. It catches this vehicle and it thinks it's the same vehicle, but it really isn't. So that's another problem we got to fix, and that's all the problems right there in this video, and we're working on it to fix it. It's stuck. And over here, Mike will talk about the directional depth of window.
All right. Originally, when given a vehicle center, it would just make a square mask around a search area around the mask and look for. Use the mask to find the most similar point to try to find the vehicle, but it's actually not very efficient because since the cars are moving, you can adjust the window to search where you predict the car to be. So if you have a center, if the search area is of size m by m, centered at the previous center, and we call the visual velocity the change just on the image. From one center to the next, we do a weighted average of previous motion, and then we use that to shift the search area. I think I actually made a better drawing of this somewhere. Oh yes, that shouldn't be there. That was a first attempt at it. But we want to adjust the search area for the similarity in the direction of the motion. So as you can see here. If this is the previous point and this is the new point, the current point, that's what we call delta x, delta y, the visual velocity, and then so we shift the entire frame, the viewing frame, to be there. So normally it would be centered around this and search this whole area, but there's not much point to search behind it because if the vehicle's moving, we can assume that it's at least stopped or gone further along. So it centers the search area around here. Like I said, the advantage is that the frame rate's pretty high in these videos, 15 to 20 frames per second. So the vehicles can't stop that quickly or change directions that quickly. So it's not likely to lose it because of looking ahead. The problem is that we're going to address next is that it doesn't actually change the size of the search area. So while it helps in finding similarities by being in a better spot, it doesn't reduce the search area, which it should. It should be able to trim off the back of this and trim these areas. Dr. Demetrius even suggested maybe doing an ellipse in the direction, something like this, which would significantly reduce them, especially now that there are times when there are 20 possible vehicles being tracked, 30 possible vehicles. So it really slows it down. So as of now, it's directional window sizing, but it's not. It's directional
in the sense of it moves it, but it doesn't actually change size. But that's next. The next, another big step that we were trying to do last semester that we didn't get to was region-based image processing in order to smooth and dilate and edge detect images, thresholding, all these things based upon the expected size of the vehicle. Originally, we just did something that would, because when the vehicles are, let's go back to the image really quick. These vehicles in the back here are I should have put a picture up, but you can, I mean, they're no more than 15 pixels wide, 5 pixels tall, and even in the color image, they all look pretty much gray. So once you blur it in order to get rid of noise, if you blur it too much, you completely lose it. But then if you don't blur it enough, you get all this noise that he showed you down here where it starts to track the moving trees. So if we can divide the image into, as he mentioned, we decided to use a neural network to get the average size of vehicles in the frame. So it would, here I'll show you. This is the first one we used, and it's a little crude now. We're trying to
Maybe explain what
yeah, it's this is being that the vehicles are, I should have put a frame in. The vehicles are larger in the corner, and then as they get further to the back, they get smaller and smaller. There's actually a better gradient than
What
that.
are the inputs in the neural network?
Oh, I'm sorry. The inputs are each edge detected image. It takes the size of each vehicle, which is within the threshold, and it takes the size and saves it to an accumulator on an array. So say a vehicle of 200 pixels is right here. It saves that size and increments a counter, so that after running it for 10 minutes, you get statistics on how often and how large vehicles are that go through each area of the image. So then you can predict with some certainty that vehicles are going to be of a certain size in certain areas of the image. We tried this. This is more of a linear prediction. We had a few that were much more complex that would actually give the road at sizes, and those may work better. This was just the first test we used, but we give the size as an input, and
I think you give the X, Y as the input. And the
oh,
size.
I'm sorry. Yeah, that's right. We do give the we're trying to get it to estimate the function that would give us the correct sizes of vehicles. But so I can't see it very well, but I tried to split it into image. This is split into 3 regions. This is actually the 3rd region. But because this neural network is not particularly good, it doesn't. This needs to be split more up here in order to get rid of a lot of noise. So it's still a little rough, but we're hoping to improve it by having it nonlinear, so that it'll actually find the roads, and then all areas outside of the roads will basically be eliminated. So which brings me to neural network improvements. It's just not like I said, it's not very effective in I mean it's much smoother than just using the pure statistics, but it's not as good as it could be. So we're going to try to introduce complexity into the neural network, to add more layers in order to really approximate the function well. For future work, number 1, gotta fix that. And then we also have to merge vehicle centers, because if closer to the front, the images, the vehicles may split into multiple pieces due to different colors of the say the windshield blends into the background. It'll think it's 2 vehicles, so we have to, based upon the expected size of vehicles in an area, we can merge centers together to get them to be the right size. Like I said, reducing the area of the adaptive window, similarity tracking based on color, improving the prediction algorithm. I'll go through these quickly, and a statistic-based vehicle identification, which is the most important. But continue to improve the neural network. I went through that too many times. Merging vehicle centers, again using color characteristics, anticipated size. reducing the area of the adaptive window, which I mentioned earlier. Similarity tracking based on color. As of now, we're just using the black and white frame. Oh, go ahead.
The problem with color is it significantly like slows down the computer. So it's I don't know if we can improve that in direction of color. But
Yeah.
I think grayscale is the best way.
And because we did it originally with edge detection and thresholding each color, and it took, I mean, even with one vehicle, it slowed to a crawl. So we may just use black and white edge detection and segmentation, and then just use the color frame to do the similarity masking. It's the next try. And then the prediction algorithm, like I said before, it just kind of takes a weighted velocity. We're going to try to actually do some kind of rule-based, if a vehicle is heading in a direction, that's important. Maybe some, not just a linear change of velocity, maybe that it take into motion, try to fit a function to the curve of the car or something. And this is the most important thing, I think, is that identifying vehicles based upon some actual statistics, as opposed to just saying, as of now, it finds the most similar mask, which doesn't necessarily mean that it's a right mask. It takes the most similar one, and then if there's a visual center identified close to it, it takes that closest center, which may be a vehicle heading in the opposite direction. As he showed when it went off the screen, it was still looking for a vehicle, and it found one going in the opposite direction and took it. So Dr. Demetrius suggested that we should take into account the velocity, the direction, the color, the similarity threshold, all these things together, and then come up with a best choice. Like the previous group said, giving him bonus points out. Try to give, grade each possible position, and then decide whether it's a vehicle or not. I would like to thank all the professors that have helped us so far. This is left over from last time. You have any questions? You went to yeah. We knew Dr. Bouchard was going to be here, so we had to.
Questions?
Is there any way you guys could eliminate that noise from the tree by possibly looking and seeing, like, the characteristic of the movement is that it's back and forth, whereas cars are moving in a line?
Have you been talking to the No, absolutely, and that's.
I already tried, but what happened was, for some reason, it was thinking also the same thing for the cars. I was getting the correct numbers,
right?
But when I try to implement it like tell it, okay, if this is moving left and right, and within the same pixel, within 10 frames, stop. Don't put a mask over it. Don't put a window over it. And for some reason, it still did.
And interestingly,
I was getting the numbers right. Like, okay, if this pixel right here, the tree was like around 200 within 80, 280, and it only increased from 80 to 85 and 200 to 205 within 10 frames, and keeps going back and forth. Stop masking it. Stop masking it with the window. It's still not working. Maybe I'm doing something wrong.
Well, also the trees move more than the cars in the background too. The trees over here, because this is a pretty windy, I mean, you can see all the rain everywhere. These trees were really like moving around. So per frame, this tree was moving more than the cars were. So and the frame rate's higher, so that it, since the frame rate's so high, these vehicles only move a couple pixels. I mean, you could do it region based, but still, yeah, it's definitely a good idea, but it's harder than we thought it was going to be.
Is there any way to get rid of the noise from the trees, like using like acceleration of some kind?
I don't know. Maybe.
The tree's gonna probably get going a lot quicker than the car would.
It's true. That's when we're talking about doing better motion prediction. That may help in that, like you said, the trees can accelerate faster than cars. So maybe that if it switches direction.
I thought I draw a tree
More
from
pixel, you know what I'm saying?
I think another problem is because it's closer to the camera, so it looks like it's
visually
moving so much.
I'm sorry.
Accelerating tree.
Like these
Save the earth right of tree.
Yes.
And you said you're doing the color directions really slow. Could you possibly do it just for one, like the red or the green and blue, just one of the color matrices instead of doing all three at once? Could possibly just do like seeing the red or you know, seeing cars with red
Yeah,
so
we-
much?
I don't think we really analyzed which one would be better, you know, it's kinda hard to pick, like, you know, cause cars vary in color so much, you know. It's like a human skin, which may be a little closer to a range, but it's definitely an option.
Yeah.
Any other suggestions or questions?
Well, the last video was in winter, so the trees were a little more pushed back, you know.
Oh.
Now we have all these.
But that's better because it gives you better case study.
Oh yeah, it's better, all right. I thought the algorithm was working great last time. I was like, look at this, it's tracking them all over the place. And then we took more video, and it's like we're tracking 50 cars in the trees, you know.
Another thing we did is we decreased the area of the window, tracking window, because we did this purposely because every time it lost the vehicle, the area of the window was so big it would track whatever's closest to it. So we try to decrease the area, and Michael was working on extending it towards the predicted path. That's it.
Thank you.
Okay, thanks everybody. That's for everybody. Okay, anybody has any questions, comments? Anything about the overall thing we're doing for Nicole? Any complaints? Now's the time to everybody say no complaints?